Welcome to the HiRSE Summer of Testing. This is a collection of tutorials focusing only on testing and is a separate series to the usual HiRSE seminar series.
Hello and welcome to the next installment of HiRSE Summer of Testing. My name is Feld and I'm going to talk about how we benefit from using GitLab's CI/CD in developing our tools. So who are we? We are a group of distributed developers located at Jülich, at Technical University in Dresden, and at RWTH in Aachen. And our tools are performance measurement and performance analysis tools, as described here on this slide. So in a performance analysis cycle, you usually start by preparing your code. We have a tool called ScoreP for this. So we insert some hooks into your application and then we run the application. The output can then be analyzed by a tool called Cube, which is a graphical tool, but the output could also be fed into the tool Scalaska, which is a weight state and root cause analyzer. Its output, again, is a Cube file. So Cube is the tool that helps us or that we use to analyze the code. Here, just as an example, this is the result of weight state and analysis of a sea ice model. You see some red dots in this right pane here. This is the Kamchatka region, and it turned out that the domain decomposition there was the cause of a huge amount of weight states. And with this root cause analysis here, we could change the decomposition and improve the runtime quite a lot. So this simulation didn't run on a laptop, although our tools are intended to run on laptops as well. But our main target are massively parallel systems like contemporary supercomputers. So yeah, we want our tools, so our products to run on these supercomputers. And when I talk about tools or products, I usually mean released tarballs. So these released tarballs can be downloaded. They are freely available under BSD license. And we intend to include everything that you as a user would need to build and install the tool on your machine. So we contain all the C, C++, Fortran source files there. So usually we have then some targets to build command line tools that are intended to run on the login nodes, and then we have some libraries that are intended to run on the compute nodes during the measurement or the analysis run. All these tools have similar build systems. So we have a configure, make, install based build system, and the tarballs are intended to have minimal build requirements. Usually you just need a shell and a compiler. And for ScoreP and Scalaska, you also need MPI and maybe additional libraries like CUDA or HIP. The documentation is also included in the tarball. So yeah, everything is there. It's really a self-contained tarball. You can download the self-contained tarballs and build them on any Linux machine. So we use Linux here because all of the contemporary supercomputers use Linux. The Cube graphical user interface is an exception here. So for Cube GUI, we also provide installers for Windows, for macOS, and for Android. So the idea here is that you do the measurement on the supercomputer. and then you copy the measurement results to your local machine, for example, to your MacBook, and do the analysis there. So the files are usually not as big. This is a quite usual approach here. Building the products, so the tarballs as part of a CI/CD pipeline is straightforward, but we want our tools to also build on HPC systems that are not as standardized as normal Linux distributions. So on HPC systems, we need to take the usually customized software stack into account. So several sites build their software stack using a tool called EasyBuild or Spec, and you select then parts of the software stack by loading some modules. And then we also need to take into account the different compilers that are available on the systems, and also the different version of the compilers. So sometimes we use some compiler internal features for our measurement instrumentation. These features change from time to time, so this needs to be detected and also tested. This is also true at the moment, at least, for OpenMP runtimes, because they added some new profiling interface there that is standardized, but not completely implemented by all of the compiler windows. Then we also need to test different MPI and MEM installations. So the MPI is not ABI compatible, so we really need to build against different versions. Same is true for the libraries that come with the accelerators. So for accelerator programming, we support CUDA, HIP, OpenACC, Cocos, and also OpenMP offloading. All of these features, combination of these features needs to be tested to make sure that our tools build on these machines and on these HPC machines and to support the mentioned features. So what we'd like to do is to do everything in a Docker container, but the HPC login nodes can't be easily replicated in a container. Therefore, we have a two-step approach in our CI/CD setup. So first, we create our tarball, our product, in a controlled Docker environment. So this is quite straightforward. Everything is controlled by us. And then we test the product on real HPC login nodes. So login nodes that expose all of these different software stacks, different compilers, different MPIs, different accelerator installations, to be sure that our tool is up to the task. In addition, we have some Docker containers usually provided by the vendors. So for example, Intel provides an one API container that is quite helpful. This comes also with MPI. AMD provides a container with ROCm, NVIDIA CUDA container. So these are used as well. And then we have a virtual machine that contains nearly every GCC and Clang version that is supported by our tools. That helps us to confront our development assumptions with reality. So how do we implement this two-step approach? So first creating the tarball in a controlled Docker environment and then testing the tarball on various machines. So we use a self-hosted GitLab instance to uh, to host our code. So here in the blue box are the different projects I mentioned earlier. And these projects are set up so that they share some common build system code, and they share some utility code, and they also share the CI/CD set. So therefore, we factored out the utility code and the CI/CD code into different groups. And so we access this factored out code in the original projects by using YAML file inclusion, which is provided by GitLab, and also by Git submodules and Git subtrees. So with respect to CI/CD, we use this YAML file inclusion. So the projects in the blue box, they have a very simple GitLab CI YAML file. So this file is the file that triggers a pipeline once you push to the repository, or you create a tag, or you push to a merge request branch. So yeah, in this file, we just include a different file from a different project, and we may set some variables. So for example, here we set the mailing list that differs from project to project. So the variables are then used in Git submodules in the CI/CD group. So these provide some generic shell scripts that not only use the variable defined in the GitLab CI YAML, but also the predefined CI/CD variables that are coming from GitLab. So, for example, CI project name and CI project directory. These variables allow us to create quite generic shell scripts that do the real job. But sometimes we also need to be project specific, so we have some shell script inheritance built into these projects. Before we come to the details of our pipelines, let me introduce our development model. So GitLab allows 3 ways to merge features into the main development branch. This is uh, via merge commit with semi-linear history, and via fast forward merge. So we decided that we want to have the merge commit with semi-linear history, so that in our main development branch, usually you just see these extra merge commits, and the merge commits then refer to the merge request, so that you always can go back and see what was discussed during developing a feature. So feature and bug fix development then happens in different branches. So here just depicted one bug fix branch and one feature branch, and you create the development branch by from an existing merge commit. Then you develop until you're ready, and then you try to merge back to the main development branch via a merge request. And only if the merge request pipeline passed and the merge request was approved by the development team, a maintainer can press the merge button This will then create this merge commit. The merge commit refers back to the merge request discussion. And so we have pretty clean history in the main development branch. So then we also have a release branch, which is it's a copy of one of the merge commits of the main branch, and usually we just cherry pick then bug fixes into this release branch until we think it's time for a bug fix release. And so here we basically have two different types of branches. So we have the release and the main branch on the one hand, and then we have this bug fix and feature branches, and they are handled differently in our CI/CD setup. So the merge, the bug fix and the feature branches, they have a special pipeline that does some other checks than main and release. So main and release, these are the ones that then run on as many HPC systems as possible, whereas the bug fix feature branches, they just run in a Docker container. So now that the development model is in place, how does CI/CD kick in? So there are several ways to trigger a CI/CD pipeline. The most common way is a git push. So you push your local changes to the repository. So you push in a branch, so a main branch, the release branch, or a merge request branch, or some other branch that is not yet part of the merge request. Another way to trigger a pipeline is git tag. So we usually just use this for releases. So we have a naming scheme for releases that helps us to later on do something specific in the pipeline. Another way is using the GitLab API, so via curl or Python. This is a maintainer-only feature. We use this to test performance, not performance, but portability-sensitive merge requests before actually merging it into the main branch. And so, this helps us to keep the main branch really in a green state. Finally, there is the GitLab schedule. We use the schedule once a week for regular pipelines. This helps us to detect changes in the HPC systems. So, for example, if after maintenance the software stack was updated, and this might affect our software. So once a week we get notified if some external changes broke our assumptions. And so here is just a screenshot of 3 pipelines. So we have 2 merge request pipelines. These are by far the pipelines that run most often. So from time to time, we then have pipelines in the main development branch in master, and also in the current release branch. So, but most of the development work then happens in the merge request. This is the reason why the most of the pipelines are merge request pipelines. Okay, let's look at what might happen at git push. So we basically have two distinct pipelines. One pipeline for pushes into the main or release branch. We call this a full pipeline. And a separate pipeline for pushes into branches that are part of a merge request. So we do different things here, and we come to this in detail soon. And in addition, we have, or we can push to a branch that is not yet part of merge request. And for these branches, we just do nothing. We cancel the pipeline. So yeah, let's look at the full pipeline. So pushes to main or the release branch. There we have 4 stages. So this is create tarball, test tarball, prepare pages, and evaluate. So in create tarball, we create our product. So the tarballs are our product. We do this in a Docker container. This is the developer perspective. Everything a developer needs is in there. So we have some modified auto tools for our build system. We have Doxygen to generate documentation. We have LaTeX also for the documentation. And we run in a controlled environment in this Docker container, and the result of this job is then a tarball. The result of the job can be either passed or failed. And so if this early job fails, then none of the other stages will run. So, but if it passed, so then the tarball is then moved to the next stage via GitLab artifacts. So all of the next stages have access to this tarball, and this tarball is then distributed to the real HPC systems, to some Docker systems, to some virtual machines. In total, we have 62 jobs in this stage. And what we do here is basically the user perspective. So this is what a user would do when he or she downloads our tarball and installs it on the local system. So here we not only have 2 outcomes, but we also have a warning outcome. So passed, I think, is clear. Failed is also clear. A warning outcome would be if the machine we want to run the job on is in maintenance. And we evaluate these 3 outcomes later on in the evaluate stage. We also create lots of log files. So if something goes wrong on the HPC machines, then we can download the log files to find out what went wrong. So the next stage would then be prepare pages. So pages in GitLab are web pages. So you can create a web page as part of the pipeline. We use this feature to create a page of, or actually 2 pages containing our products, our tarballs. So for the Summer official tarballs, it looks like this. So we have our latest tags. So these are the releases. We also list the release candidates here. The page also refers to the commit. So you can click on the commit and go back to the GitLab user interface. Yeah, you can download the tarballs. and you can directly access the documentation either in HTML or PDF format. Then we have also tarbals for the master branch. There we keep the 3 latest ones on this page, and we also have the latest ones from the release branches. A second page is created for the development tarbals. So these are tarbals created from the current merge request. So this is basically the same content here. So you have the commit you can click on. You have the tarball to download. You can view the documentation. In addition, you can click on this merge request number and directly go back to the merge request discussion. As you see here, the pages do not only contain the tarball of the current pipeline, but also tarballs of previous pipelines. So we actually need to have some persistent storage to store information from previous timelines. So we have a special machine for this that has for every project has a persistent storage. So here we just show the SCORP one. We have 2 subdirectories, so branches and public. So under the public sections are the the releases. So we have the tarbals there, we have the documentation there, and some metadata to then generate the HTML file. And then we have the branches subdirectory. There we have the master branch and the release branch highlighted. So if we have a pipeline running here, a master pipeline, that will then add one tarball and its metadata to the master subdirectory. We keep up to 3 tarballs for master and for the release branches, but this can be specified by a variable in the GitLab CI YAML file. So, and in the last stage, in the evaluate stage, we then look at the results of the test tarball stage. So how do we do this? We do this by GitLab artifacts. So the test tarball stage creates some small text files. So for example, if we finish on the machine, so if the machine is not in maintenance and the job ran and it finished within a time limit, then we write a file called finished in time, and with this file we then can in the later stage detect if the job ran. For example, if the machine is in maintenance, this file is not created, and we can detect that there was a timeout. Not only if the machine is in maintenance, but also if we ran into the GitLab's project timeout. And we don't detect this as a failure, but as a warning. So if we have a real failure, then we also communicate this via a file, so failed job and some the job name attached, and with these 2 files, so it's finished in time and this failed job, we can in the evaluate stage determine if the pipeline is green, yellow, or if it failed. And in case of warning of failure, we then send an email to the developer mailing list. If the job succeeded, if it passed, then nothing is done. This evaluate stage does something special for releases. So releases follow a naming scheme. This is the way we can detect if we are running or if we are running the pipeline for release. We automatically then create a GitLab release entry and also link to the tarball on the page's website. So this is done fully automatically. So that was it for the full pipeline. Now we come to the merge request pipeline. So remember, we have two distinct pipelines, the full pipeline and the merge request pipeline. So in the merge request pipeline, we don't run on any supercomputers. We just do stuff in controlled Docker containers. And we also use the persistent storage also for generating pages. But let's start at the preparation stage. So this is just for our convenience. We use the GitLab API to collect some metadata for this merge request. So for example, we collect the files that were changed, that were added, that were removed in this merge request. We also collect the set of commits that are part of these merge requests, and we store this data in a text file and make it available as GitLab artifact to the next stages. So next stage would be the prerequisite stage. Here we check some coding conventions because we want only merge stuff into the main development branch that adheres to our coding conventions. So we have this beautifier job here that uses a tool called uncrustify to check if our indentation conventions are met. For some projects, we also check the copyright. We complain if there is trailing white space. For OTF2, we have this some signature checks here. And at the moment, we are working on a check for the ABI of libraries. So this in future might help us to decide if a merge request could be part of of a bug fix release. So bug fix releases shouldn't change the ABI of libraries, but it's manually not so easy to check, but this hopefully can be automated, and this would be the next step. So you can add prerequisites stuff here as needed, and all these jobs then rely on the metadata collected in the preparation. So once the prerequisites are met, so we go to the next stage, to the create tarball stage. You already know this from the full pipeline. This is basically an identical job. We even use the job description from the master branch by GitLab or by YAML include mechanism. So this is really the same as in master, so that we don't have any inconsistencies between merge request branches and the main branch. If this create tarball succeeds, we go to the prepare stages. page as prepare pages stage as described before. So as we are in a merge request pipeline, we add then a tarball and the corresponding metadata to one of these MR subdirectories, and then again create from the entire directory structure, we create the website. So in total, this for Scorpio, it's 1.7 gigabytes. So quite a lot of tarballs and documentation and metadata that is lying in this persistent storage. Yeah, finally, we have an evaluate stage here, which is different from the one in the master or in the full pipeline. So yeah, if we have a failure, then we notify the author of the merge request and not the entire development team. Okay, so I think that's it for the merge request pipeline. So again, we have two pipelines. So we have the full pipeline running on first creating the product, the tarball, then running on the supercomputer systems, creating pages, then doing the evaluate, and we have this merge request pipeline doing some prerequisite checks, then creating the tarball, then doing creating the pages, and also have this evaluate step. Yes, and once the merge request is approved, so we just, or a maintainer of the project presses the merge button, and then the pipeline in the main development branch is triggered. So then running the full pipeline. Okay. What else do we use GitLab or GitLab CI/CD for? So yeah, we have this persistent storage here for our pages, and from time to time if a merge request got merged, so there's basically no need to keep the tarball and the metadata around. So we have a cleanup job. This is in a separate branch. So this is just for doing the cleanup via a GitLab schedule. I think this is done once a week. And this then loops over the entire directory structure and uses the GitLab API to check if the merge request is still open. So if not, like here in the last page, in the last line 60, so we remove this entire directory. So nothing to do here manually. So this is quite nice. So there's even more. So we have regular meetings with our distributed development team. So we create meeting invitations. So we send an email to the developer mailing list, and we have a GitLab wiki page. So we here also use a GitLab schedule to create this wiki page. And we, within this meeting create update job, we use the GitLab API to collect the merge requests and the issues that were created or merged in the last week. So this was a very quick walkthrough of how we use GitLab CI/CD for our projects. So the good thing is that our projects are similar structured so that we can really refactor or factor out common code that really helps us in maintaining the entire setup. And yeah, what we created here is basically we have two pipelines, two different pipelines, one for the main branch, one for the release branch. They do something different. So only the main and the release branch run on HPC systems. Um, we do something special for releases. We can detect if HPC systems are in maintenance. Um, we distinguish between tarball creation or product creation. This is developer view, and using the tarball on the HPC systems, so the user view. We yeah, put all the created tarballs on web pages, so which are publicly accessible. Also, the development tarballs, so that if you work together with the project partner or with someone who has access to some special system, you can provide a tarball and ask the users to try the development on their system. We created some small helpers to clean up our intermediate storage, and we also have some small helpers to yeah, remind us of our meetings and also to collect some data um, that what actually happened in the last week of during development. So that's GitLab's CI/CD infrastructure actually is our lives as developers. Yes, by all means. So this is really helpful for us. But setting the entire system up isn't so straightforward. So I skipped quite some layers of indirection that pose some daunting implementation challenges. So we actually have shadow CI/CD projects for each of the projects listed here that then contain machine and module-dependent job configuration options that then execute the generic scripts I mentioned earlier. Yeah, when setting it up, we had great support by our GitLab admin Anke. So she provided us with a GitLab mirror as a test instance that restarted every night. Coming to the end, I'd like to thank our funding agencies that made the work on Scorpii, Scalaska, Cube, and the related projects possible. So thanks a lot. And also thanks to the colleagues at Technical University in Dresden, who also contributed to the CI/CD work presented here. And finally, I'd like to thank the organizers of HiRSE Summer of Testing, Claire and Robert, for inviting me giving this talk. Yeah, thanks a lot. Take care and bye-bye.
Thank you for watching this tutorial. Please check out the slides on Zenodo, linked below, and see you next time.